All right, let's talk about the invisible high-speed data zooming right through your living room. When you're kicking back on the couch, seamlessly streaming a video or downloading a massive file to your phone, it honestly feels a little bit like magic. But today, we're going to break down the incredible physics and engineering that actually make this modern miracle possible.
We all easily understand how a physical cable connects a router to the internet. You see the wire, you plug it in, and it just makes intuitive sense that data flows through it, like water through a pipe. But here's the big question. How exactly do raw zeros and ones leap across that invisible air gap between your device and the Wi-Fi access point? I mean, you can't exactly throw a 1 and a 0 into the air and just hope it lands in the router, right?
So let's jump right into Section 1, the missing network cable.
To replace that physical wire, we use a pretty logical three-step pipeline. First up, you've got your device's digital data, just pure ones and zeros. Then we run that data through a highly precise process called modulation. And finally, that process transforms your digital data into a physical radio signal that literally flies through the empty space in your room.
Which brings us to our second section, how digital data becomes radio waves.
Let's zoom in on that middle step for a second. How on earth does a digital 0 or 1 actually alter a physical wave? Well, Wi-Fi operates on radio frequencies. And just to put the scale of that into perspective, 1 gigahertz means a staggering 1 billion cycles every single second. So imagine a continuous radio wave oscillating through space. By intentionally tweaking the amplitude, the height of the wave, or shifting the frequency or phase, we literally embed our digital ones and zeros right into the wave itself. That technique is what we call modulation.
Now, modern Wi-Fi takes this concept and cranks it up with a technique called QAM, or Quadrature Amplitude Modulation. Instead of just tweaking a wave for one bit of data, QAM lets us pack multiple bits into a single wireless symbol. You've probably seen terms like 16 QAM or 256 QAM. The rule of thumb here is simple. The higher that QAM number, the more bits you can efficiently cram into a single pulse, assuming, of course, you've got a strong, clear wireless signal. All right, moving on to Section 3. Bands, channels, and avoiding traffic. Now that our radio waves are packed with data, let's look at the wild physical environment they have to navigate. It's a busy place out there. Wi-Fi operates across different frequency bands, mostly 2.4 gigahertz, 5 gigahertz, and recently 6 gigahertz. And it's all about trade-offs. The 2.4 gigahertz band is awesome for punching through walls and going the distance, but man, is it congested and prone to interference. 5 gigahertz? That gives you wider bandwidth and much faster speeds, but the signal fizzles out way faster over a distance. And the newest 6 gigahertz band provides a massive new spectrum for ultra-low latency, but it is incredibly sensitive to physical barriers. So no single band is universally better. It completely depends on your usage scenario. Oh, and here is a super crucial myth to bust right now, because it trips up almost everyone. When we talk about 5 gigahertz or 6 gigahertz in the context of Wi-Fi, we are strictly talking about the frequency band of the local radio waves. That has absolutely nothing to do with your cellular 5G mobile network, where the G simply stands for generation. Kind of a fun trivia fact, but definitely an important distinction.
Now, within these frequency bands, the available spectrum gets sliced up into smaller segments called channels. Think of the main band as a massive highway, and the channels as the individual driving lanes. Your device essentially picks a lane. But imagine you live in a packed apartment building, and 50 different routers are all trying to merge into the exact same lane. You get a massive traffic jam, just pure interference.
So, how does Wi-Fi keep from collapsing into total chaos when, say, 3 phones in the same room want to transmit at the exact same time? If they all just shouted at once, nobody would understand a thing. To solve this, Wi-Fi uses a protocol called CSMA/CA. It essentially forces devices to be polite. The rule is literally, listen to the room before you start talking. If the channel is busy, you wait. If it's clear, you go ahead and transmit.
Which leads us perfectly into Section 4, Technologies Breaking Speed Limits.
Because engineers weren't just satisfied with politely waiting in line to speak, they've invented some absolutely incredible tricks to squeeze mind-blowing speeds out of thin air. Take OFDM, for example. This tech takes our highway lane and slices it into dozens of tiny parallel sublanes, or subcarriers. Thanks to a math property called orthogonality, these subcarriers can be packed incredibly tight without stepping on each other's toes. Then there's MIMO. Ever wonder why your router looks like a robotic spider with all those antennas? Well, multiple antennas let the router broadcast totally separate spatial streams of data at the exact same time. We call that spatial multiplexing.
So let's update that original pipeline of ours. Now, your data doesn't just get modulated. It gets hit with high-density QAM, chopped up into parallel subcarriers by OFDM,
routed out to multiple antennas via MIMO, and then finally broadcast through the air. These technologies stacking together is the real secret foundation of high-speed modern Wi-Fi.
But what about when things go wrong? Say you walk behind two thick concrete walls and your signal drops. Your Wi-Fi doesn't just quit, it smartly shifts gears. It drops down to a lower, more robust modulation rate and cranks up the error correction. It's a feature called Adaptive Modulation Encoding, or AMC. You might sacrifice some top-end speed, but you basically guarantee your digital data actually survives that harsh environment and arrives perfectly intact.
Let's take a look at where all this is heading in Section 5, Wi-Fi 6 and 7.
This relentless push for spectral efficiency brings us right to the latest, greatest generations of wireless networking. When you hear about Wi-Fi 6 or 7, it is not just about shiny new frequencies. These iterations introduce vastly smarter ways to share the airspace. Wi-Fi 6 brought us OFDMA, which slices channels into smaller resource units so multiple devices share the medium way more efficiently. And Wi-Fi 7? It takes a huge leap. We're talking massively wide 320 MHz channels, an upgrade to hyper-dense 4096 QAM to cram insane amounts of bits into a symbol, and multi-link operation, which actually pushes data across multiple bands simultaneously.
All right, let's wrap this up with Section 6, Invisible High-Speed Communication.
Let's zoom all the way out and trace the entire journey from your couch to the internet, bringing all these concepts together. Here is the full transformation. Your phone's digital data, those pure ones and zeros, is meticulously modulated into an electromagnetic wave. That wave travels through the physical air, dodging interference, bouncing off your walls until it hits the router's antenna. The access point's receiver grabs that physical wave and carefully demodulates it right back into perfect ones and zeros before sending it off through the wired internet.
When you kick back and watch a video load instantly, it really does feel like invisible magic. But as we've seen, it's not. It is brilliant physics, highly efficient spectrum management, and decades of engineering, all working in perfect harmony. It's literally just electromagnetic waves combined with digital modulation and strict MAC protocols.
Which actually leaves us with a pretty fascinating puzzle for our next explainer. We just saw how Wi-Fi constantly has to listen for traffic to avoid data collisions in the air. But if wired Ethernet is also a network, why did it completely abandon its own collision detection system years ago? How exactly does a data packet speed through a modern corporate LAN without crashing into everything else? Join us next time as we plug back in and trace the wired journey. See you then!